Welcome to Colloquium. Before I introduce the speaker, I'd like to ask if there are any announcements that anybody has. That's a no. All right. Well, it's a pleasure to introduce today's colloquium speaker, Dr. Madison Myers from Montana State University. Madison received her bachelor's degree from the University of New Hampshire, where she was emphasizing geochemistry, I believe. Then she got her master's from the University of Idaho, where fieldwork played a prominent role in her research. I made that up, is that
yeah,
right?
That's fine.
Okay. Madison received her PhD from the University of Oregon, where she studied one of our favorite things, the volatile elements in volcanic glasses, where she was using this as an effort to deduce eruption rates. Volcanologists in general face a really tough challenge because after an eruption, it's kind of difficult to know what led to that event. And examining the erupted material can sometimes lead to really confusing results. Now, Madison has worked really hard to identify the least ambiguous materials, and you have a great paper on how to analyze melt inclusions and prepare them, for example. And she lets thermodynamics and kinetic arguments be her guide to interpreting these observations. Speaking of observations, she believes in careful observations and is personally responsible for Montana State University being accepted as a member of the Yellowstone Volcano Observatory. Her work is really well regarded, leading to multiple research grants from NSF, including a very prestigious Career Award for Young Investigators. I'm looking forward about the volcanic eruptions. We're learning about the volcanic eruptions at Yellowstone, perhaps the most important volcano in the lower 48. So, Madison, take it away.
What a plug. Thank you. All right, well, thanks for that introduction. And for those that want to know a little bit more about my work, is this sounding okay? Okay, feels weird here. So most of my research has focused on studying things like fall deposits. So this is an example of a deposit from an explosive eruption. And most of the questions that I'm trying to answer have to do with what is the accumulation history, the storage conditions, and the timescales of eruptions. And as Rick mentioned, mostly I have approached this by using volatiles, namely water, CO2, sulfur, fluorine, chlorine, and lithium, to understand the processes that are happening within these volcanic systems, specifically focused at the melt. So for instance, here, these crystals, like you literally can see melt inclusions in them. That's how, what? Oh, the mouse, fine. Okay, look at that. You can see melt inclusion, big screen, very nice. Okay, so here is a melt inclusion, which is a little blob of melt that is entrapped in a growing crystal. And so I've often looked at what the chemistry of these melt inclusions are compared to these open melt pockets, which we can call embayments or reentrants. I didn't do it, I swear. Cool. In order to understand processes. And I often pair this with mineral chemistry, experimental petrology, and field work in order to understand different processes, mostly within caldera-forming eruptions, but I've also worked in kind of arc-setting eruptions as well. And I just wanted to emphasize that today's talk is not really going to focus on this beauty thing here called the melt embayment. But tomorrow I'm going to give a talk on Magma Ascent, specifically focusing on the reliability of this tool to understand how quickly these magmas are coming towards the surface. So essentially looking at different volcanic systems, comparing it to other tools, as well as using an experimental approach. So if you're interested in this, I hope to see you tomorrow. So here's just some beautiful footage, some eye candy to start out our day. This is an eruption from Calbuco in Chile from 2015. And I think the wonderful thing about this footage is that it reminds us of how beautiful volcanoes can be, how deadly they can be, how scary they are, and just how impressive in general they are to watch. I think like this could get anyone interested in studying a volcano. But the challenge for someone that studies large caldera-forming eruptions is that we often are able to observe and learn from these smaller events, and we're often trying to upscale the processes that we've learned from these events to larger systems, which we never get to visually see erupt, like thank goodness, but also kind of a bummer. So, if you are thinking of it in terms of meteorology, where we might want to put monitoring equipment on here, make a hypothesis, create a model, try to understand what kind of triggered the eruption and what was going to happen next, these smaller eruptions really benefit from their frequent observations. Whereas larger volume systems, and this is just a silly schematic here from Cashman and Gordiana from 2014, there's several open questions as to how these systems might accumulate, meaning why don't they erupt earlier? Why are they allowed to get to such large volumes? How do you trigger these eruptions to occur? There's a lot of kind of literature out there that suggests that they don't just, like on the schematic here, you're seeing that we have, all right, so here's just gas, some recharge event happening. We have gas bubbles. At one point, it triggers a dike towards the surface, forms kind of a plume, and then eventually, once enough material is let out, you have caldera collapse. However, there's a lot of evidence to suggest that the thermal structure and the size of these larger systems might have different triggering mechanisms that are not classically called upon in the smaller volume eruptions that might change how we might monitor or understand the progression of these eruptions. In addition, I would say that oftentimes when you talk about these and in textbooks, we envision a continuous process where the eruption just starts, it continues to form, big plumes, maybe ignimbrites, and this leads directly into caldera collapse. However, what if there were eruptive pauses? We see eruptive pauses all the time in eruptions that we're actually able to witness. How would we essentially see this in older deposits that we don't have any evidence for what happened over time? What if there were multiple magma chambers or multiple vents even? What if these kind of eruptions are essentially going along long dike features rather than a central conduit? How does that change how we model things like the plume behavior or where hazards might evolve over time? And so essentially, I kind of came into my, at the end of my PhD, really trying to understand, well, what evidence can we use to kind of quantify these types of complications? And this is the type of research that I'm still pushing forward with my lab group today. We, as Rick mentioned, are part of the Yellowstone Volcano Observatory. So unlike all of the other volcano observatories in the United States, it's a consortium of 9 different state agencies and federal agencies that monitor Yellowstone volcano as we know it. Here's just a view within Yellowstone, so quite beautiful. But essentially, our role, I would say, is to try to answer these questions. How do we understand the timescales of the processes that are occurring? However, most people think this is my job as part of the Yellowstone Volcano Observatory. And there's some clickbait going around right now, so don't click. But essentially, I get asked this question several times a year. And that's really maybe what my role is in Yellowstone Volcano Observatory, is just a buffer for Mike Pollan dealing with the general public. But a lot of the work that we've been doing, the resolution of this is a little rough, but is essentially trying to go around Yellowstone and remap areas of the park, understand the volumes that we're looking at, and try to repiece what's happening underneath Yellowstone. So for instance, one of my master's students, Natalie, has been charged with looking at trying to make a higher resolution geologic map of Yellowstone, because there's currently 27 separate maps that make up Yellowstone, and they don't typically agree along their shared borders. So that's one of the roles that we're serving in the Yellowstone Volcano Observatory, really trying to determine the pre-eruptive configuration, the timing of different events, how extensive these different events are. And we're really at the point in Yellowstone where we're still just splitting up different units and recognizing that we may have lumped together things that are actually separate events. So again, this is the challenge of studying kind of older silicic systems. So just some background. So Yellowstone National Park is outlined over here. Essentially, it was the first national park founded in 1872, about 150 years ago. And as part of its foundation, this painting, among others, by Thomas Moran was formed. And so essentially, when the white settlers of the day were going into Yellowstone to undertake their kind of first quote unquote scientific discovery, they very wisely brought some painters with them in order to capture how beautiful this area was, to convince the East Coasters that they should make this a national park. However, along with this beauty and a lot of really crazy stories, we have to recognize that there were people living in Yellowstone at this time. And so essentially for 11,000 years, many indigenous tribes used Yellowstone for hunting and trading, where this tribe depicted on the right, the Tukadika, lived in Yellowstone all year round. And so essentially the kind of white settler tour of Yellowstone and the formation of Yellowstone as we know it today essentially resulted in all of these tribes being relocated out of the park, many of them murdered and killed, and a lot of poor rhetoric going around to kind of spread lies to allow and justify people's actions at this time. And so if you're interested in these topics, I would suggest this book. It's called Empire of the Shadows. It is by a white scholar, but he does a very nice job of pointing out when the story that we have put forth around the formation of Yellowstone National Park is essentially very skewed by the perspective of who wrote the story and the narrative. In addition, in Yellowstone, there's a lot of beautiful areas that are named after some pretty shady characters. So on the left-hand side here, this is Mount Duan. He was the lieutenant that is best known for murdering over 300 indigenous women and children. This peak has been the #1 peak that they wanted to rename in Wyoming for over a decade, and it just happened last year. So very exciting. And this QR code on the left-hand side here, you can look at it, and this is an initiative to rename several of our landmarks in the United States that have kind of fraught names. The right-hand side, that's Hayden Valley, again, beautiful area, but named after a huge sample collector, right? There's a huge gallery in the Smithsonian associated with the Hayden collection, but he also was pushing this rhetoric that indigenous people were lesser kind of and allowing some negative actions to occur. In addition to that, here's another QR code of a cool project that's happening right now that a lot of people in Montana State University are associated with, and this is called the Bison Relocation kind of program, where they're actually moving bison back to reservation land as part of projects to teach indigenous students that were, or indigenous kids, essentially, that had not learned how to process the buffalo. And so they're moving these bison over there, and this is a cool project that you can go here to learn more about or donate. So with this history of what Yellowstone is, as we know it today, it's also good to note that it is 9,000 cubic or square kilometers, which is about the size of Puerto Rico. All right, so this is a huge area. And essentially in the 1960s to 70s, they undertook mapping the whole park. This took about 5 summers. So, you know, take or leave how much you think that they were able to map this park. It has over half of the world's active hydrothermal features, about 10,000 different active thermal features, 1,000 to 3,000 earthquakes annually. Most of them, of course, are under a magnitude 3. They're very low magnitude. And it also is home to one of the world's largest caldera centers, meaning that kind of collapse feature that forms after enough magma leaves the system. And so the major eruptions that make up Yellowstone are kind of outlined here in the green and in the purple. Essentially, these are massive eruptions. Does anyone in the room know the volume of the Mount St. Helens eruption? Cubic kilometer, right? So what we're looking at here is you just multiply it by an easy 2,500, right? So imagining a Mount St. Helens eruption and then trying to upscale this to the volumes that we're seeing here for the 3 kind of larger caldera forming eruptions becomes no easy feat. And in addition, we often talk about the fact that there's 3 caldera forming eruptions where there actually is a 4th one. It's the baby at 50 cubic kilometers. And it formed the west thumb, sorry, I have to find my mouse, of Yellowstone Lake. So this is actually a caldera, but essentially almost none of the eruptive products can be seen today because it's been covered by subsequent lava flows. So essentially for those that might not study these eruptions, there's kind of 2 main products that I'm going to talk about today. So one is from the explosive eruption, which are these plumes going up, and that plume from Calbuco. These are fragmented materials that are going into the air, where a little pumice clasts are going to fly out of it that are rapidly quenched against the cold air. And those are usually what we use to try to understand things like volatiles, because we expect that they haven't experienced any kind of post-depositional changes to their chemistry. However, we often are seeing, and especially in Yellowstone, massive ignimbrite. So these ground-hugging flows that go out, they stay hot for a really long period of time. And so you kind of just have to take different thoughtful approaches to being able to study both. They lead to really different deposits, where on the left-hand side here is a fall deposit where you can see that it's well sorted and graded, where on the right-hand side, this is an ignimbrite. And you can see large kind of pumice clasts, some lithic clasts in kind of a matrix. So really different types of products that we're looking at. So in order to understand caldera systems, we often go to kind of case studies of the systems where we have more information. And so I would argue that one of the best studied caldera systems in the world is the Bishop Tuff in California. And so this is located in the eastern part of California, and we know a lot about this system. We know the temperature it was stored at, the pressure it was stored at. There's evidence for compositional zonation or kind of different magmas that were tapped through this eruption. There's amazing detail as to the timescale this eruption occurred over, where it's thought based on the fall and flow dynamics that erupted within 5 days. So again, lots of information associated with this eruption. And one of the coolest ones, I think, comes, at least in my opinion, from Wilson and Hildreth, where the lithics around the Long Valley caldera are so unique that they were able to actually repiece in stratigraphy where the vent was at any given time based on what lithics were associated with within the rock. Meaning that, like, if you saw some glass mountain rhyolite, you could tell that this was probably the vent source and that the Ignimbrite was coming out from that region. And so from this, they were able to see things like the unzipping of the caldera and integrate that in with all of the other information to understand kind of the unraveling of this system. And that's our ultimate goal, is really to understand what are the processes that must have happened so that we can either make a model or try to understand what the future might look like for these caldera systems. Because essentially, it's very likely that we don't even really know where the next caldera forming eruption is going to be. I would argue, though, that this is because the exposure for the Bishop Tuff is beyond belief. All right, so this is a very famous deposit where you can see the fall at the bottom. In the middle, you'll notice, anyone in the audience? What's the middle? Anyone? Oh, I thought so. Ignimbrite, yes. All right, so there's Ignimbrite lobes coming in, fall at the bottom, and fall at the top. So the importance of this, and then another Ignimbrite on top. The importance of this was to suggest that you can actually have fall and flow occurring coevally, which was a big change in how we understood caldera-forming eruptions. And again, a lot of these kind of groundbreaking understandings of caldera dynamics come, I think, mostly from the Bishop Tuff. In contrast, here is one of the nicest outcrops from Yellowstone. All right, so you could see why maybe we're not quite at the same place as we are for other caldera-forming events when we're trying to work in Yellowstone. And so this can be a really challenging process. And between this and the 5 years of field mapping that really were undertaken, I think there's still a lot of work to be done. So for instance, one example, these are essentially maps of where all the Ignimbrites from the major Ignimbrite forming eruptions of Yellowstone went. So on the top, we have the Lava Creek Tuff. It's broken into 2 different members, Ignimbrite members, A and B. Clearly, Christensen really liked this kind of A-B strategy. And then there's the Mesa Falls Tuff, which is just thought to be 1. And then the Huckleberry Ridge is broken into 3. And so the importance of this is that the idea behind how Yellowstone worked was that it was one cooling unit, meaning everything came out sequentially. You had one Ignimbrite come out, then the next one came out, then the next one came out, and that there was no kind of time break, that you were just having consecutive Ignimbrites spilling out of the center. However, Colin Wilson spent about 20 years mapping the Huckleberry Ridge Tuff, and from that found that this was potentially an oversimplification. So based on a lot of field work, what he found was that there are kind of weeks to months or maybe years to decade long time breaks between each of these eruptive members. And in the fall deposits that I studied, we see evidence for kind of this week-long process where you have cross-bedding and water reworking, again, suggesting that there are multiple start and stop events associated with this eruption. But again, the challenge is that a lot of the evidence that Colin has from field work, you could take with a grain of salt. How do we trust that this is actually something that happened? How do we quantify this? And so this is a big kind of task that we're trying to undertake in the community. And so here, to start off, kind of how we've approached untangling how these Ignimbrite and caldera forming eruptions occurred. Well, we start with the fall deposit. And so this is the fall deposit that you can find for the Huckleberry Ridge Tuff. It's the opening event. And what you might see here is that we have cross-bedding, and we have an area just above the mouse where you see kind of what looks like maybe rainfall. And so this was the evidence to suggest, okay, maybe the plume stopped at some point at the onset of this eruption. So why is that important? Well, what that means is that the overpressure feeding the system was able to cool off enough that you weren't continuously pumping out material into a plume. So that suggests that a very different kind of dynamic than we typically imagine for some of the largest eruptions on Earth, where you kind of just think that they're going to go, and once they start, you wouldn't be able to stop them. But that seems to maybe not be the case. So a lot of what I developed that Rick was mentioning about timescales of processes were associated with trying to figure out, well, how do we figure out the time associated with these deposits? And so to do so, essentially, we kind of took single subset layers where we were looking at pumices, single glass shards, and quartz-hosted melt inclusions and reentrants to understand what was the chemistry looking like and what were the time scales associated with potentially water and CO2 movement in this system. So I'll talk more about the time scale aspect tomorrow, but today we're going to focus more on the chemistry, specifically for the melt inclusions and the reentrants. So I promise I will only show like 4 geochemical plots, so bear with me. So for these 2 plots on the top, we're looking at rubidium versus uranium and chlorine. All of these are essentially incompatible elements in a crystallizing rhyolitic melt, meaning that their concentrations will increase as you continue to crystallize in the system. And so essentially what this is showing us, each one of these color or triangles represents a melt inclusion, and the colors that are kind of warmer at the bottom here, these are essentially the most evolved, right? And so essentially the first material out, which you can see in the bottom left-hand part of the slide, is that these kind of lower units are the most evolved first out. And so in many ways, this is representing what we think of for caldera-forming eruptions, where the most evolved material, the highest water content is the first thing that spits out of the system, and then it becomes more or less, oops, sorry. I gave away my thing. Less evolved as we go down. But one of the things that became really exciting was starting to look at trace element ratios, where we started to see that these melt inclusions actually formed separate clusters rather than continuous like lineations. And so what does this mean? Well, essentially clusters mean that you have crystallizing magma that is separated from each other, that you're not within chemical connection from one kind of melt body to another. And so using statistics based on kind of cluster analysis, we were able to break up the melt inclusion population from these fall deposits into 6 different kind of populations, where 3 and 4 in this plot would actually split apart really easily based on CO2 content. So what this suggested to us is that we actually had separate crystallizing bodies, some of these representing a pure composition. So like quartz population 1 is the first layer that came out that was the most evolved, but some of these other ones are made up of maybe a couple of different layers. However, you might be asking, all right, so this is just the same plot, different populations, but saying that like, well, these are quartz populations, these are crystallizing populations, this might not actually be representing of what the chemistry was looking like upon eruption. And so that's a good point. So melt inclusions are the composition at entrapment. So this might be telling you that you had separate bodies that were crystallizing at the beginning, whereas the reentrant or the embayment, this is open to the external environment. So it can actually diffusively re-equilibrate with changing conditions. And so we decided to see, well, did this collapse at all in the terms of chemical diversity by looking at both reentrants and co-erupted obsidian pyroclasts. And so when we did that, we noticed that we did get a collapse, that we've gone from maybe 6 populations that are being observed down to kind of 3 fruiter populations. And so we kind of took this to suggest that there was 3 main magma bodies that had taken in these different quartz grains through some kind of restructuring at the onset of this eruption. We can look at this in pie diagram space if you like pie diagrams. So on the left-hand side, this is quartz populations, where the bottom pie diagram is the base of the eruption. And what you can see is that you kind of have some shifts that go up, where you again have these like purples at the bottom and you go more towards orange reds at the top. But some of these populations are kind of messy within each one of the layers. The right-hand side is showing you essentially what the embayment reentrants are doing, as well as what the obsidian pyroclasts are doing. And so we see this systematic change in the composition as we go up this fall deposit, which was pretty cool. And the most important aspect to kind of keep in mind is that no single glass shard taken from this whole deposit has a composition that doesn't fall into one of these populations. And what we took this to suggest was that we actually had separate vents feeding the onset of this eruption, where there was 3 separate magma bodies that were being tapped either simultaneously or sequentially at the onset of this eruption. And sometimes they're closing off and other times they're kind of starting up. A really interesting kind of dynamic for what we think the beginning of this eruption was. And so putting that in context with the regional setting for the Huckleberry Ridge Tuff, where there's these major fault zones that are kind of intersecting the caldera system, and the timescale information, which I didn't show you, but essentially shows that there's very kind of sluggish opening ascent rates associated with this eruption, had us build this model where essentially potentially a fault or a dike system is intersecting with maybe different composition magmas that are physically separated to explain the chemistry that we're observing, and that sometimes one of these is being tapped and other times multiple are being tapped at the onset of this eruption. And so we took this to suggest that more of an external triggering mechanism or like regional tectonics controlling the opening phase of this eruption, which allowed things to potentially start and stop, meaning not driven by internal overpressure of the magmatic system. However, we then, of course, questions, new data always leads to new questions. So then we were curious, well, what happens once you start going into the Ignimbrite? Right? Is this just like these separate little melt bodies that are over a larger homogeneous kind of system? So with that, this kind of was taken over by another student. I left and went and did a postdoc. And essentially what he found was that he was able to see the same 3 populations using matrix glass and feldspar. And so then he decided to go into the basal Ignimbrite. So looking at something called vitrophyre, which is rapidly quenched basal material of the Ignimbrite. And what he found, so this is another trace element plot, was that he also found these statistically separate little populations of glass from these many locations around the caldera. And that instead of collapsing in terms of the diversity, it just expanded. So we found 5 additional pockets. And so this is really suggesting that we had multiple discrete magma bodies feeding this eruption for the entire time, at least in the opening kind of A member phase of this. And because of the fact that there's kind of no linearity to these, it seems like they are separate evolving crystal bodies. When we look at the distribution of them, so these again are pie diagrams. I guess we went through a pie diagram phase, but the idea being that here are the 8 different compositional clusters that we're seeing from the matrix glass of these basal vitrophyre. And if you look at the pie diagrams, each one of these represents a sample that was taken and the chemistry that makes up that sample. And so what we could see is that there's no real rhyme or reason into how this caldera forming eruption opened, where there's no clear trend where you're seeing a purple zone or an orange zone or a yellow zone. It's kind of a hodgepodge of material going everywhere. And so this was interpreted to suggest that caldera collapse was somewhat early on in this eruption, where you were then mixing all of these magma bodies in the vent and they were erupting out with no kind of rhyme or reason as to where they were going. And so this is not quite as tidy as the Bishop Tuff in terms of the chemistry that we're seeing in the lobe kind of nature of the Bishop Tuff. And so coming back to kind of the opening figure, where this is the silly cartoon of how we kind of originally thought caldera forming eruptions occurred, I think that the Huckleberry Ridge Tuff is kind of more of this lens model where you have multiple vents that are active and intersecting, allowing for really different kind of sub-chemistries to be coming out of this system, which makes more sense because geophysically, we never image a large, big blob of melt. This is not a stable configuration. And so I think as a community, we're going more towards this idea that melt is probably stored more in these lens fractures and that we're seeing that evidence in these fall deposits for this feature. And so essentially the Huckleberry Ridge Tuff went away from kind of a simple like sequential Ignimbrite mode of just kind of like changing chemistry that we might have expected from the Bishop Tuff. And now we have evidence that there was multiple vents, there was multiple magma bodies, there were major time breaks between different phases of this eruption. And so it's really a very intricate kind of system compared to what we have for many caldera forming eruptions. So pretty cool, largely maybe because of the fact that it is massive and covering a huge area. And so melt would potentially collect in separate isolated pockets. I'm then going to switch gears to the question of, well, how does this compare from the Lava Creek Tuff? All right, so the Yellowstone in general is a nested caldera system. It still has an active heat source under it today with, depending on what type of tomography you might favor, might have up to 20% partial melt under it currently. So there's still a lot to be done on the Huckleberry Ridge Tuff in crystal-specific studies of understanding how these magmas may have come together. There's a really interesting mafic isotope story of what was feeding these eruptions. But essentially, I decided maybe with COVID to pick a local project, and the Lava Creek Tuff is kind of what we thought of. All right, so what do we know about the Lava Creek Tuff? Well, essentially, most of the sampling, I will say, that has happened for the Lava Creek Tuff has come from 3 primary locations: Tuff Cliff, Virginia Cascades, and Flag Ranch. The eruption age has been really well constrained because it's a marker bed around the world. So I think people have really spent a lot of time of really understanding how old this eruption is. So it's around 630,000 years old. It's currently broken into 2 members, A and B. And I will say, just kind of a heads up, this eruption. So Bob Christensen went into the field, it sounds like in the 90s with Colin Wilson, and he was like, you should study the Huckleberry Ridge Tuff. The Lava Creek Tuff is horrible. And essentially when I started at Montana State, Colin's like, you should study the Lava Creek Tuff. It will be great. And it's really a challenge. And so I would say that most people don't really agree that there's an easy way to distinguish between A and B. And so likely what I will end up doing is deleting these 2 terms from our vocabulary, because we have, out of 150 samples we have collected, we probably have found 2 samples that contain amphibole. So this is not, I would say it's a trace element, and it should not be used as a diagnostic feature. In addition, this unit was also mapped of having no evidence for time breaks between the eruption of these 2 members, much like the Huckleberry. And so these 2 members are also thought to be essentially kind of slightly zoned in thermal space of 2 magma sources. Most of the evidence for 2 magma sources comes from the amphibole being present in one and not in the other, meaning you need a different magma. But again, not sure that is actually necessary to call upon. Bulk Ignimbrite, which there's not a lot of that data, but it's not super useful, essentially suggests that they're overlapping. And zircon and sanidine, which again were mostly used for age dating, have been also looked at for their trace elements, and it suggests that they're recording very similar histories between what is marked as A and what is marked as B. And so even though there's no simple schematic drawn for what the Lava Creek Tuff eruption might look like, when I was starting to read through this, I essentially was like, well, maybe it is a blob. Like, it just sounds like a blob. There's no really clear distinctions for what's happening within it. It might be somewhat thermally zoned and slightly compositionally zoned, but no real drastic differences. But again, I largely think that's because of how many samples were taken of this 1,000 cubic kilometer material. It, of course, all became enticingly more interesting with the new study that came out in 2018. So Bog Creek had some new mysteries to share with us. So essentially, as I mentioned, Colin Wilson decided to remap all of the Huckleberry Ridge Tuff, which meant that he went to every single map deposit of the Huckleberry Ridge Tuff in Yellowstone and in Idaho. And so this one right here, shown in the purple, essentially was mapped as the Huckleberry Ridge Tuff. And when Colin went out there, you can read in his field notes something along the lines of like, question mark, question mark, question mark, what is this? This looks nothing like the Huckleberry, but this isn't the Lava Creek Tuff, like question mark, question mark, question mark. All right, so essentially this unit looked nothing kind of like he had recognized the Huckleberry to be, and it looks nothing like the Lava Creek Tuff, which is why Christensen originally mapped it as the Huckleberry. 2 Ignimbrite units were then sampled and essentially age dated, and it turned out to have the same age as the Lava Creek Tuff eruption. So, all right, that's a little kind of new piece of information, but they look nothing like the Lava Creek Tuff, meaning that they actually have things like scoria in them, and there's no scoria found in any other aspect of the Lava Creek Tuff eruption. Interestingly, these 2 new deposits, one is this beauty of an outcrop that I showed you earlier, and the other one is actually found as chunks of solidified ignimbrite in a breccia deposit. All right, so what does that mean? Well, essentially, a breccia deposit is a near vent deposit, meaning that you had to have a local source that was kind of breaking up the rock. But the fact that the age of the Lava Creek Tuff is this solidified chunk of ignimbrite suggests that you essentially had to have made an ignimbrite, cooled that ignimbrite, and then got to the point of being able to break it to put it into a breccia. So what that suggests all of a sudden is that we have some kind of separate eruption, a time break, where it's the same age from our age dating techniques, but it had to have actually erupted, cooled before it could be broken and then emplaced here as another unit of the Lava Creek Tuff. Another kind of fun new study that came out is from your own group here. And so essentially Shamlu and Till in 2019 went to Flag Ranch and looked at things like sanidine and quartz grains and found these bright rims. These were inferred to represent a triggering mechanism. That was actually a pretty fun piece of news that went around the United States, where they had evidence to suggest that this kind of ramping up period occurred over the periods of months. And so this is an interesting idea of what these are representing in the system, but the challenge becomes, well, these bright rims are only really found in the upper portion of the Lava Creek member A and the basal fallout of member B. So they're in a very localized part of the eruption. And we now have all of these new units of the eruption that have a different time span that probably aren't associated with what this is in this kind of inferred trigger mechanism. So the question starts to become, well, how do we integrate this understanding of these bright rims from this one part of the deposit with what we're understanding as a more long, complex eruption? And so essentially, this is kind of the goal of what Rick mentioned is the career grant. And so we're trying to reevaluate the pre-eruptive configuration and eruption progression of the Lava Creek Tuff to compare against the older Huckleberry Ridge Tuff to try to understand how are these eruptions maybe similar or different, and how is that going to inform us moving forward? The challenge, again, with the Lava Creek Tuff is that we can't do it in exactly the same way. And so one of the reasons is that the glass in the Lava Creek Tuff is completely rough. It's very much been vapor phase altered, meaning that we can't do the same kind of glass analysis that we were using in the Huckleberry to kind of repiece the whole story. So instead, what we started with was just doing a really intensive sampling. So there's probably even more spots than are showed on here. We essentially tried to take representative samples of the new Ignimbrites within Bog Creek, stratigraphic sections of A, quote unquote, A and B, to try to understand, is there an A and is there a B, as well as any single pumices that we could find and a few samples of vitrifier. And again, the goal is essentially to use things like minerals and glasses to start to repiece what the eruption dynamics are in a similar fashion as the Huckleberry Ridge Tuff. And so this is done by my students Stacy Henderson and Ray Salazar, and I'm going to share a little bit of their kind of preliminary results on this project. So essentially, Ray, being a brave Coloradan, was game to undertake remapping the Sour Creek Dome. All right, so this is a really remote area where the only place that is accessible by trail is essentially here, the most western part of it. This is about a 4-mile hike in, and then the rest of this is essentially what they call a bear corridor, and has no actual camping area. So Ray spent the last 2 summers working on trying to remap the extent of this new unit. So on the left here, this is the old map where you can see the Huckleberry Ridge Tuff. Here's Bog Creek. Here's essentially where it's been mapped. And so what you see now on the right-hand side is everything that is in this kind of peach color is now the new unit of the Lava Creek Tuff. And so what we found is that there's been a lot of mismapping in this whole area. There's essentially, this is a photo of it, and you can see that there is the scoria class in it, which is very different than what the rest of the Lava Creek Tuff has in it. And so we think this is a pretty dominant unit within the region. We haven't been able to go over to this east area because, again, it's very hard to access, and we're trying to do a helicopter permit this year to do it. But the most exciting thing from his work probably was the finding of what this sample is right here. So this was mapped as a lava flow, but as we started sampling around this area, we find Hiami in this unit. And so essentially we started to think this might be a localized hotter source of the Lava Creek Tuff. The age date just came back like 2 weeks ago, I think, and it confirmed that it is the Lava Creek Tuff. So essentially we have another new unit that we're trying to fit in. The challenge right now is that we don't really have a way to put this in the stratigraphy. So it's very challenging for us to understand if this is before or after the main Ignimbrite units of the Lava Creek Tuff. But one interesting piece of evidence is that the breccia deposit, which is up here, the sanidine chemistry from it, which is mostly what we're using to try to unravel what is happening in the system, matches the chemistry of a Lava Creek Tuff A unit. So we might have a geochemical connection there. The other important thing to kind of note is that here, the welding intensity increases up to around this star. And this star is essentially what we might infer as a vent source, just like this breccia is also kind of requiring a near source vent in order to produce it. And the caldera boundary currently is mapped way over here. So we're thinking that this is actually evidence that the caldera boundary needs to be moved inward, or that we have a separate kind of caldera collapse, like a sector collapse event happening within this system. The other thing that we've been doing is essentially using sanidine. So this is just trace element compositions in sanidine, so orthoclase versus barium. And so this is Stacy's work, where she is essentially trying to do this in like rock units all around the caldera. And the most important thing to kind of take away from this is that we're starting to see kind of color compositional clusters here, not as striking maybe as what we were seeing in the melt chemistry of the Lava Creek Tuff. But what we're taking this to suggest is that this sample dependency, meaning that if you took a sample from Tuff Cliff, it mostly falls here, whereas if you take a sample from Grizzly Lake, it's here, suggests that we might actually have lobes of material tapping slightly different magma bodies that are coming out way more organized than what we were viewing in the Lava Creek Tuff. And so this really suggests that we're getting kind of sector compositional zones of magmas with this composition coming out and distributing in this location of the caldera versus some magma coming out and distributing in another location. So this is a big difference from what we're seeing in the Huckleberry, where it seems like maybe we have some kind of melt pocket scenarios, but largely what we're seeing is compositional dependent kind of tapping of magma systems going around the caldera. And so kind of bringing this back to big picture, we did a review study 2 years ago on kind of just, is there a model for how we can imagine what a super-eruption looks like? And essentially, this idea of these separate melt lenses, again, is gaining traction in that the more kind of super eruptions that we're studying, the more we're seeing evidence for these separate bodies being tapped. Whereas there's also the kind of end member of a stratified magma system that seems to be less representative of what we're seeing in the system. In the Huckleberry, we're seeing also kind of like a chaotic tapping of this, kind of start-stop eruptions. And essentially in the Lava Creek Tuff, we also see maybe some early evidence for some separate melt bodies. We also are seeing evidence for multiple different kind of start-stop, or at least Ignimbrite cycles. But we're definitely seeing a more orderly fashion in which the magma is coming out. And so that could suggest maybe later caldera collapse, allowing Ignimbrites to come out of their kind of vent sources, more similar to what the Bishop Tuff was potentially doing. So we're thinking that we're going to go more towards a Bishop Tuff model for understanding how the Lava Creek Tuff eruption is coming out, where we're going to try to use sanidine to understand lobes and connect different magma sources around the caldera. The best part of this grant is really student involvement. All right, so I would say that Yellowstone is a challenging place to be a volcanologist, especially one that likes volatiles, where everything is so hot here, it really ruins the volatile record. But it's been a great opportunity to bring undergraduates into the field, teach them about field safety, teach them about making observations and that things are not set in stone. There's a lot of newness to every place that we go, where we think we're gonna see one rock and we end up seeing another. And with Natalie Craig, who was given the daunting task of updating all 27 geologic maps of Yellowstone, not a great master's project, besides how much you might learn about the park system. But essentially with Natalie, we really started thinking about kind of DEI space in field studies. So essentially the cost of field education can be a barrier to diversifying the geosciences. In addition, it's not the same experience for everyone, where there's a lot of exclusion that different kind of identity types have felt with participating in field work. So Natalie and I really wanted Yellowstone to be a space where everyone, even though it's scary, there are bears, it's hard work getting out there, we really wanted to try to not have this be a limitation to people being able to explore this beautiful area. So in the summer of 2021, we essentially established a volunteer field hand training program where we offered smaller intro field experiences to over 20 undergraduates at Montana State University, as well as some external users. And so what this allowed people to do is fill out a form with it and answer questions like, what is your experience? How long do you like to hike? Do you like front country? Do you want to experience back country? And we did essentially training programs to help them kind of get used to what they were going to experience. And in addition, we created a lend-lease program for field equipment to allow students to have unburdened access to expensive field gear. And so this was something that we really enjoyed doing, and most of the students, I think, had a really wonderful experience, even the ones that got charged by a bighorn sheep. In addition, we also ran a bystander intervention and field safety course. This is through Advanced Geo, and I'm sure many of you have participated in this. It's an excellent course. But essentially, the biggest kind of takeaway from this was that harassment does not have to be illegal to have damaging consequences. And so we often talk about physical, kind of like sexual assault in terms of the types of things that we're trying to avoid with field work, but there's many other things beneath the surface where that are essentially bullying behavior that can be really exclusive to different people. And so we're really trying to find ways to encourage bystander intervention in how we do field safety when we send students out into the field. And so I would encourage you to also check out this, essentially the last QR code I have. It's a report of a workshop that promoted safety in field sciences. It's a really nice report in that they break down different strategies to promote inclusiveness, and they also break it down by the amount of effort that it would take to implement it and the cost that it would take to implement. So it's a nice way to kind of visualize field safety. So with that, I will take any questions, and thank you for your time.
We were taking questions, and I saw one from the second row up.
I don't know if that's on.
I was just wondering, so with the 6 different, thank you, with the 6 different quartz populations that come from unconnected bodies, did that correlate at all to hand sample texture heterogeneity or lack thereof?
Yeah, great question. Well, so the quartz populations, I think that a lot of that was just crystallizing in the chamber, and then that there was kind of a amalgamation, like these two may have merged together in these two, but then essentially everything kind of came out in a fall deposit, right? So it's like fragmented. It's not like we essentially sampled what were loose crystals in different layers, not single pomi. And so I do think, based on like some of the diffusion modeling stuff that I did, that some of the crystals within individual layers had different ascent histories and maybe different paths associated with them, but like how homogeneous kind of each layer was in terms of those melt inclusions or embayment or obsidian even suggests that they were definitely tapping the same kind of source, that they just may have had a different decompression pathway. But that didn't lead to any major textural differences. We did start to look at pumice, and so, you know, like pomi, micro pumice essentially, but there weren't, again, strong differences in that except for like maybe conduit controlled processes.
I have a question about the your heterogeneity within the glass.
Mm-hmm.
Like, how much did you actually map to be able to figure out that there was homogeneous glass, and like how much would you have to map to find mixing?
Yeah, so that was Elliot that mostly did the glass. I was all on the inclusions, but essentially I think he did like 3,000 shards from the fall deposit, and I think he did like several points and transects across them and never found any kind of shift. So I don't know if you need to do that many in order to feel secure about it, but I definitely feel secure in what he did. So.
So I have a question about the post-caldera activity. And so I like your picture of this complex connected mesh of different bodies.
Mm-hmm.
How do post-caldera events relate to that subsurface picture, and how do different pockets get activated that might be smaller volume?
Yeah, that's a great question. I think that, so, you know, in the nice thing about the Yellowstone Volcano Observatory is that we have these like bi-weekly meetings and people share research that they're doing in Yellowstone. And I do think that like Mark Stelton is thinking more in these spaces of like understanding with Carrie Cooper and a couple of grad students of like what are the post-caldera magmas really showing us? Because I think a lot of that was just done in age dating space, and now they're trying to get into it in compositional space. And so it seems as if there are still kind of melt pockets even being tapped within these smaller eruptions, which is kind of interesting. I think that it seems like there's almost similar kind of variations of tapping in the small systems and the large systems. Like there almost seems like they're similar processes, except for the scale is completely different. And so that I don't understand why we were talking about this last night, like what is controlling a small body, like growing in this way that maybe it's tapping multiple things and it's erupting is a lava flow versus not doing that and stopping and building to a large enough volume that you create a caldera forming eruption. And I mean, you could say some generic things on like flux rate and thermal heat kind of input controlling those boundaries, but I don't think we have a great understanding of what is fully controlling that kind of relationship.
There is just a comment from online. Professor Steve Simpkins says he's sorry he couldn't attend in person, but especially wanted to thank you for your discussion of indigenous title and relationships to the Yellowstone region, as well as the fascinating volcanology.
Thanks for that comment.
Right here. So I want to follow Amanda's questions about the magma chamber, plural probably. I'm still struggling to understand what volume this magma is entering into. What was there before? You know, it's hard to visualize what the terrain, what the rocks were prior to the incorporation of magma. I mean, there wasn't some big empty chamber that just got filled up. So what is your vision for what that looked like? Yeah, you know, for what these chambers look like.
Yeah, I that's a great question. I think I often think of it in terms of I guess I always think of it at the beginning of melt kind of coating around crystals and then like coming together in kind of these like separate regimes where you might have melt percolating into one area and forming a lens of some sort that might be in a crystal kind of structure, and that you just have a lot of these. But the fact that you have to have maybe like tens of cubic kilometers of material that have very similar composition then suggests that at one point that you do have to have like a pretty active melt framework, or you're extracting it really quickly. I mean, there's a lot of evidence to suggest from like New Zealand systems that melt could be stored kind of more within a crystalline framework and then extracted over a very short time period and erupted. So that's where I think more crystal specific work would probably start to elucidate that. And we just haven't gotten to that stage yet in Yellowstone to see like what is the crystal recording about its like extraction eruption kind of journey. So that's.
But does there have to be assimilation of the existing country rock to accommodate that volume?
Not necessarily. So there are isotope studies that suggest that you don't need a lot of assimilation potentially, especially of the earlier stuff of country rock. The Huckleberry Sea actually has quite a bit of contamination of the local country rock. And there's also evidence from oxygen isotopes that as you kind of go through the caldera sequence, that the older caldera or the younger caldera eruptions are remelting some of that earlier material, which makes it easier to generate a bunch of rhyolitic melt. But again, the scale that we're thinking of here makes it like you almost need to call upon several of these different kind of mechanisms, and getting to the point where we have a coherent story, it's kind of like hard to imagine how many samples you need to take before you get there. But good questions. Oh, cool. Just compliments. How wonderful.
I have a follow-up question on just the observation of volcanoes. Are the people noting a lot of inflation before eruption? Do you see the surface rising up?
Well, in Yellowstone, actually, Yellowstone is interesting in that it's inflating and deflating like at crazy rates all the time. And so that's kind of its normal background level because of the high hydrothermal system that is active there. So I don't necessarily, you would have to see something pretty drastic before you would start to be concerned. I think that's the nice thing about having, 30 years plus of monitoring data is that you can start to understand what is background and what is unusual. But like we did a Yellowstone volcano simulation this last year of like what an event would look like. And it was definitely, it started actually with bison being killed by CO2 fluxing, which was kind of cool. But you have to start seeing like really strong earthquakes before it seems like people would be probably concerned. So it seems like earthquakes would be our first kind of signal that something was over deformation, at least for this system.
I don't detect any more questions, so let's thank our speaker again.
Hey. Class dismissed.